the Congress, the House and Senate in 2008 passed a law to add additional flight to deliver alpha magnetic spectrometer to this International Space Station.
This audio recording was made possible by organizations working together for people, not profits.
After that, many people continue to visit us. I remember him spend the whole afternoon with us and try to understand the new technologies we developed for space. And after that, I decided to be more friendly to NASA. And so this is my support of the Shuttle Commander Mark Kelly, who is now running to be a senator. I hope he succeeds. He's an awfully nice person. That's me. And so it was launched into space on May 16, 2011, and the two MIT alumni, Michael Fink and Greg Chermatoff, Dr. Dole, remember certainly him. So in 8 years, over 135 billion cosmic rays has been measured by AMS. So let me show you some of the latest results. First is the origin of cosmic positons. There are three sources of positons. You have explosion of stars, produce protons and helium. When they travel through space, interact with other protons and helium, produce positons from collisions. If you have dark matter, when they collide, they produce positons. And you have a new astrophysics sources, unknown one, such as pulsar, will produce positons. So there are three sources. Because the great interest of positons and electrons, before AMS, there were many measurements. And this is electron spectrum, this is positron spectrum. Looking at this spectrum, you notice the data not exactly agree with each other, has very large errors. When the data has large errors, it's very good for theoretical physicists because you can make many theories. And most physicists assume that the flux is equal to a constant times the energy to the gamma's power. Gamma is known as the spectral index. So this is called the power law energy dependence. Our measurement based on 1.9 million positons, and this is our measurement. And this is, everybody believes positons come from collision. And this explains the low energy part and what happened to this. Cannot be explained by existing theory. And so we finally found out the positron spectrum is the sum of a low energy part from collision cosmic rays. Another is a new source or a new astrophysics source or from dark matter. The most important thing is when you fit this to any formula, you have a cutoff energy, 1 over exponential 1 over ES, meaning after a certain energy, you're no longer going to see positons. And that is a very peculiar effect. So at low energy, the data come from collision cosmic rays. At high energy, it's from a new source or from dark matter, but has energy cutoff. Indeed, now we sit there for days and we don't see any more positons at high energies. Another very curious thing, which I forgot to report to Maria last time, and that is antiprotons and positons have exactly similar behavior. Antiprotons are a very rare object in space, and it goes up and tends to be flat. For electrons, this is based on 28 million events, spectrum goes up, goes down. If you analyze more carefully, you will see it comes from two power laws. One called power law A, one called power law B. what does this mean? It means low energy, the contribution of cosmic ray collision, this is the green part, cannot explain the measured data. And this is different from positrons. A positron, you remember, a low energy positron can come from collision. But for electron, it cannot. It can only be described by a power law. At high energies, electron do not have a source term nor a cutoff, and for positron has both. Therefore, electrons and positrons are totally different. Electron, you can continue to measure the high energy. Positron, after certain energy, it disappears. Now let me share some results with you on cosmic nuclei. There are two types of cosmic rays. One is called primary cosmic ray, proton, helium, carbon, oxygen, and so forth. They are produced during the lifetime of stars and then accelerated by the explosion of stars. Another type is called secondary cosmic ray, lithium, beryllium, boron. They are produced by the collision of primary cosmic ray with the interstellar medium. So there are two kinds. Now, what is the difference between these two? First, let me talk about protons. This is the measured proton data for many experiments before AMS, and the data again do not agree with each other, has very large errors. So traditionally, physicists assume the flux is still constant times energy to the gamma's power. This is our measurement proton, the red point, based on 300 million protons. At low energies, it does agree with traditional assumption, traditional theory, but above this energy, you have unexpected increase, meaning the theory is no longer correct. So the proton flux cannot be described by a single power law. Before AMS, there were many results on primary cosmic rays, helium, carbon, oxygen, from balloons and satellite experiments. If you group them together, you have a random pattern, and you do not know what is going on, mainly because the error is so large. This is our measurement above 60 GeV. 60 GeV, the primary cosmic rays have identical rigidity dependence for helium, for carbon, for oxygen. And you have one energy dependence, another energy dependence. They deviate exactly at this point. This is very strange. Cosmic rays are totally different things, but their energy dependence are exactly the same. Then there are secondary cosmic rays. Lithium, beryllium, boron also have identical rigidity dependence. This is lithium, beryllium, boron, and they are different from primary cosmic rays. Therefore, in space, all the cosmic rays across the periodic table have only two classes. I think it's unthinkable such a thing could happen. And so let me mention what we're going to do on the space station until 2024. That's the lifetime, projected lifetime of space station. One is complex antimatter, like anti-helium, anti-carbon, anti-oxygen, and then try to pin down the origin of positrons, the electrons, and antiprotons, precision study of solar physics, and continuous study of heavy nuclear. Let me share with you some thoughts about complex antimatter. The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning, because before the Big Bang expansion, nothing exists, so at the beginning it must be equal amount of matter and antimatter. This experiment is orders of magnitude more sensitive than previous experiment to look for antimatter from balloons and satellites. This is an antimatter candidate. This is measure the track in the bending plane, in the non-bending plane, looking from the top, measure the velocity. This signal has a charge -2. The mass is exactly the same as helium. Helium, of course, charge is +2. So you just begin to see antimatter. Such a thing cannot be produced from cosmic ray collision. The rate in AMS for anti-helium candidate is less than 1 in 100 million helium. At this extremely low rate, more data is required to further check the origin of this event. 1 in 100 million is a very, very small number. You absolutely must make sure it's correct. And anyway, nobody is foolish enough to put another magnetic spectrometer in space for the next 20 to 30 years. So we have time to check this. And the next question is, what's the origin of positrons, electron, and antiproton? Today, we know at high energies, the positrons has energy cut off, but we do not know if it is from a new source or from dark matter. A new source and dark matter I will explain. The question is, what is the new source? Why do positrons vanish at high energy? The red point are the data we have now, and the green one will continue to take data to 2024. What is most important is to go to very high energy data. A new source could be pulsars. Pulsars emit light, and the light interact with the pulsar magnetic field, produce positrons to high energies, and it's continuous without energy cutoff. A light ray do not produce antiprotons. Antiproton cannot come from pulsars. So this is the projected antiproton spectrum. This is what we measured and extended to 2024, compared with the positron to 2024. Such a spectrum cannot come from pulsars, because pulsars do not produce antiproton, because a photon doesn't produce proton antiproton. Then what is dark matter? Remember your high school physics. If you have a galaxy and you have a region of observable mass, and then you have at a distance r, you have a star rotating in a closed orbit. A closed orbit means the force on the star is zero. That means gravitational force and centrifugal force must be balanced. And therefore, you can calculate the velocity of this star must equal to m of r, the total mass inside, divided by r. And so this curve will be from gravitation, assuming all the mass you can see. And this is the measured curve of a galaxy. That means there's a large radial mass you cannot see. So the existence of dark matter is not in doubt. What is dark matter? Collision of dark matter produce positron antiprotons. Dark matter particle has a mass m, and they move slowly. Therefore, collision of two particles produce a total energy of 2m. So dark matter collision produce antiprotons and positrons. For conservation of energy momentum require positron antiproton energy must be smaller than m, and therefore there's a sharp drop-off at the mass of m. That's a unique signature for dark matter. So this is the red point to show measurement, and this is a dark matter model. You see a sharp drop-off, but the error is still very large. Even though it's a good fit, you cannot say you have seen dark matter. You need to see this point in order to make sure it drop off. And this is why it's so important to go to this point.
I'm the captain now.
This audio recording was made possible by organizations working together for people, not profit.
I still don't know how they did this.